Okay, so for 3-4, you can tell that what we're going to focus on today are perpendicular lines. So we just did some constructions of perpendicular bisectors. So remember that it says that your perpendicular bisector is a segment, or of a segment, is the line that's perpendicular at the segment's midpoint, which makes sense because the midpoint is the place that cuts the segment directly in half. So if this is my midpoint, look at the things I notated on my picture. Okay, so the first thing, if it's a midpoint, pay attention please, because this is stuff you're going to have to label yourself. If it's a midpoint, you're going to draw the two dashes, and that means that they're congruent. Okay, the little box in the corner, Naomi, what does that represent? A right angle. Okay, so if it's perpendicular, you're going to see the right angle symbol. If it's a bisector, you're going to see that both sides of that are equal. Okay, all right, then the next part says the shortest segment from a point to a line is perpendicular to the line. Okay, so you've probably heard the shortest distance from 2 points is a straight line. Okay, it is actually a line that is perpendicular. Okay, so again, we need to start making those connections that if it's perpendicular, then Nate, what are you going to see? If something's perpendicular, what do you know you're going to see?
They're gonna be next to each other. They're gonna be like oh wait, no, they're gonna be like connected.
Okay, but in particular, what are you going to see in your picture? Like, how do I know that?
Like a right angle.
Yeah, you're going to see the right angle, right? That's how we know these two are perpendicular to each other. Okay, and then you have an example. It says, given the drawing, name the shortest segment from A to BC. And we're going to draw that picture in. So you can use either part of your straight edge that you have. So this is your picture that we're going to use. Okay, so this is going to be a line. Okay, on your line is going to be BC. So just pick a point B on that line. And we won't construct it, but we are going to draw this so that it's perpendicular. So I'm going to have a right angle. And this is A, B, and C. Okay, and AB I want you to label as x minus 5. AC I want you to label as 12. Okay, so it says name the shortest segment from A to BC. BC is your line, so I'm going to put my line symbol above that. Okay, so remember we just talked about that the shortest segment from a point to a line is perpendicular to the line. Okay, so Jillian, what are you thinking about for part A? Okay, so it would be AB, right? So to the line BC, it would have to be AB. And Jillian, how did you know it?
Because it has 90 degrees.
Okay, good. So that's the segment that has the 90-degree angle with BC. Now for B, it says write and solve an inequality for x. When you're writing an inequality, do you guys remember what symbols an inequality has? Okay, yeah, less than or greater than, less than equal to, greater than equal to. Okay, so there is one thing that we know about these two sides that are given. So you are given AB is x minus 5. You are given AC is 12. Remember that AB is the shortest segment to BC. So AB has to be less than what other segment? Nope. So let's talk about why. So remember, this is 2 BC. There are two segments that go to BC, AB and AC. We know that AB is less than AC because it's perpendicular, so it's shorter. So now what we can do is set up the inequality. So AB is x minus 5. AC is 12. So when it says write and solve an inequality, you already did the first part. So this is your inequality. And now we're going to solve it. So remember, with inequalities, you basically solve them like equations. There's really only one special rule you have to remember when you're solving. Do you guys remember what that is?
If it's a negative, you have to flip a sign.
When?
By or multiply.
Yes, okay, good. So if you multiply or divide by negative, you have to flip the sign. That's really the only special rule that it has. Everything else is going to be like an equation. Okay, so now we know that the value of x has to be less than 17. Okay, now I told you we were learning some new theorems today, so here they are. So we're going to talk about a few things in them. Remember that each theorem is going to have a hypothesis and conclusion. So we're going to talk about that too as we discuss these theorems, so that we can figure out how we're going to use these if we have to use them in a proof. Okay? So for our first theorem, it says if two intersecting lines form a linear pair of congruent angles, then the two lines are perpendicular. Now, what is here is going to be like the reason that you would write in your proof. You'd write two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular, which I know is a lot. This one has a particular name, which is helpful. So if you have two intersecting lines that form a linear pair of congruent angles, let's talk about what that means. Okay, they form a linear pair of congruent angles. So, Clara, if we have a linear pair, what do we know? And what else? Good. Okay, so linear pair, they're going to be two angles that make up a straight line. Together they have to be 180 degrees. Okay, their sum. Okay, now if they're congruent angles, Nia, if we have congruent angles, what does that mean? They're the same. Okay, so if they're the same and they add up to 180, Griffin, what do they have to be? Why? So step before that. Well, what do the two angles have to be? Yeah, right? Because if their measures are equal and together their sum is 180, we know that both angles have to be 90 degrees, right? Okay, so that means this has to be 90 degrees and this has to be 90 degrees. So the conclusion is then the lines are perpendicular. Okay, and then here I just said because 90 plus 90 is going to equal 180. That's the linear pair. This is the part where the angles are congruent. So this is your given information. Then we know that they are perpendicular. And of course, we know that they're perpendicular because you have the 90-degree angles. Okay, so this could be used to prove that lines are what? What's the final result? The lines are perpendicular, right? Okay, so it could be used to prove lines are perpendicular. Look at this one. Okay, if you look at the conclusion, it says then it is perpendicular to the other line. So if you were using this in a proof, it would be to show that the lines are perpendicular. Now this one is nice because it has a specific name. This is the perpendicular transversal theorem. Okay, perpendicular transversal theorem. So that would be your reasoning in a proof. Let's see what conditions this has to satisfy. So it has to be that a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line. So that's what we showed in our first activity today. When you are using this in a proof, you could write perpendicular transversal theorem. Okay, so for perpendicular, you can go ahead and abbreviate that. So if a transversal, in this case, your transversal would be Q. And then look at the picture. You just know that it's perpendicular to one of the lines. Your conclusion is that it's perpendicular to both of the lines. Okay, so this would be your conclusion. This is what you would be given. Your conclusion would be, here's N, here's P. We know that these are parallel because we have the little arrows in them. And then Allie and I were just talking about this a second ago. Allie, how do we know that the lines are parallel based on these two? Their corresponding angles. So to prove these are parallel, you could use what? No, but you're close. What is it? It's not the corresponding angles postulate. What is it? Yeah. Yep, so the converse of corresponding angles theorem. Okay, so that could be something else that you could use. Okay, and in this case, because they are 90 degrees, you have 90 degrees here, you'll have 90 degrees there. 90-degree angles are going to give you perpendicular lines. Okay, so you still can use some of your old theorems that you have. All right, and then the last one says if two coplanar lines are perpendicular to the same line, okay, so you'd have to have two lines that are coplanar. It doesn't say they're parallel. If they're perpendicular to the same line, then the two lines are parallel to each other. So this would be used to prove that lines are what? Parallel. Good. So if you're trying to prove that lines were parallel, this would be something that you could use. So this would be what you are given. And then your conclusion would be same setup, only difference is you would have that the lines are parallel. Sorry, that's kind of small. Okay, so I just put in the symbol for your parallel lines. And if you were using this in your proof, you could say two lines are perpendicular to the same line, so your two lines are going to be parallel to each other. again, another way that you could use this is you could also say, what? Yeah, you could also use the converse of the corresponding angles theorem. Okay, so you also could use the corresponding converse of corresponding angles postulate. And that's because you know corresponding angles are congruent. If you know that, then the lines have to be parallel. Okay, so this would be helpful, like if you were given that they were both perpendicular, and then you could jump to that conclusion. Okay, so we are going to do a proof together. And yay, we get to fill the whole thing out. Okay, so we're going to write a 2-column proof. We are actually going to split up the two given statements. So if you look at the first given statement, it tells you that EHF is congruent to angle HFG. That's given. And then we can put our final step in there too. EH is perpendicular to GH. It really doesn't matter if you put all the givens in the same step. The only reason why sometimes we put them in separate steps is because each one of these is going to lead to something else. Now, whenever I put something in my proof, I want to mark that off in my diagram. So if I say that angle EHF is congruent to HFG, I'm going to label that. So I have HFG right here. Okay, I'm going to have to draw this line in here. I feel like it should have already been there, but it wasn't. Okay, so I have EHF, and then I have HFG. Okay, those are given. Now, you can see that these two angles form a special relationship. Max, what kind of angles are these two? So of our four types, right? Yep, they're alternate interior angles. So if they're congruent, what do we know? Okay, so yeah, they're going to be the same. We already have that. What else? If we know two angles are congruent, what can we show is true? Ryan, do you have an idea? If alternate interior angles are congruent? Good, okay, so if the two angles are congruent, we can show the lines are parallel. Great job. Okay, so we're going to look at the two lines that are going to be housing these alternate interior angles. So it would be this line here, EH. Okay, and EH would be parallel to FG. Okay, now once that happens, I put that in my diagram too, so I'll put like my parallel lines. And then that's going to be because of the converse of the alternate interior angles theorem. Bless you. And then remember I said we're going to split up our given into two separate statements. So this is FH. And this really should be like this. GH. Okay, so FH is perpendicular to GH. So if that's given, the FH is perpendicular to GH. It really should say FG. Yeah, you have GH. This should be FG. Sorry. And because they have it right here in your diagram.
You can't see the diagram. It's on the sheet.
Thank you. I didn't. This one was on there. I just highlighted it. So like your FG and your GH. So again, that one was given. So we're going to use one of our new theorems. So let's look at what we have. So we have parallel lines, and one of them is perpendicular. We're trying to prove that the other one is perpendicular. Yep, good. Your perpendicular transversal theorem. So if you have parallel lines and one of them is perpendicular, then the other one has to be perpendicular too. Okay, so that's your perpendicular transversal theorem. You can write it out, or you can write the symbol. All right, and then we'll just keep practicing those so we can get better. Your homework is actually worksheet packet. Okay, so I will hand that out to you. And then if you borrowed a book or a Chromebook, you go ahead and